Maybe I'll just keep it. All right. Let's go. Okay, so what I want to finish up today is I want to finish up talking about harmonic functions, because that's going to sort of close up our study of derivatives, right? So what we're working on right now is the study of complex derivatives, and everything we've talked about falls into the category of complex derivatives, right? Cauchy-Riemann equations is a study of derivatives. We define complex differentiable. We talked about what it means to be holomorphic. And so harmonic functions and the construction of harmonic functions sort of finishes up our conversation about derivatives. And then we're going to start talking about integrals. So probably on Friday this week, we'll start talking about complex integration, which is exciting because complex integration is cool. I mean, all the stuff is cool. To me, anyway, so I'm going to remind you guys for a second sort of what we talked about last time. So if f of z is a holomorphic function, then the real and imaginary parts of f, why am I writing words? This is why we invented symbols. Then the real part of f and the imaginary part of f are harmonic functions. Recall that a harmonic function, a function is called harmonic if u of x and y is a real valued function and uxx plus uyy is equal to 0. So it satisfies Laplace's equation. And then the other thing we talked about last time were the Cauchy-Riemann equations, which said that f holomorphic, gotta be careful, f is holomorphic if and only if for f of x plus iy is equal to uxy plus iv of xy, we have ux is vy and uy is equal to minus vx. And so to sort of put this together, it's actually worth taking a second just to do a quick proof that a holomorphic function has harmonic pieces. So we can do that real quick. So let's prove this. So this is a theorem, TM. So I didn't actually prove this last time. I kind of went through it because we were at the end of class when I talked about this. If we assume that f is holomorphic, then one thing that we get out of the fact that f is holomorphic is that its pieces are C whatever, right? So u, in particular, u of xy and v of xy must be C1. I mean, they have to be. If the function is complex differentiable, then certainly the pieces of the function have continuous derivatives, or it would fail to be holomorphic. Also, f satisfies the Cauchy-Riemann equations. Holomorphic means 1, that the pieces are C1, and 2, that f satisfies the Cauchy-Riemann equations. So what you do is you just write down the Cauchy-Riemann equations and then differentiate them. Yep.
So this proof is for that.
This proof is a proof of this theorem. So this is proof of theorem. And I wrote down this bit and this bit because we're going to use them both. What we're trying to show is that this is true, and what we're going to use is the Cauchy-Riemann equations. Okay? All right, so we just write them down. Certainly it's the case that ux is equal to vy, because that's one of the Cauchy. Did I say vy? Okay, I wrote vy and said it, so that's good. And uy is equal to minus vx. And so you just take some derivatives. If I take the x partial derivative of this equation, so take the x partial derivative here, and you end up with uxx is equal to vyx. And if you take d by dy of this equation, of course, when I say d by dy of equation, what I'm saying is take the derivative of this. If the functions are equal, their derivatives are equal, right? That's really all we're saying when I say that. So it's just shorthand for that. So the y derivative of uy is uyy, and the y derivative of vx is minus vxy. Oh man, that is so close to what I want. If only vyx and vxy were equal to each other. By Clairaut's theorem, which remember last time said that mixed partial derivatives of nice functions are equal to each other, vxy and vyx are the same. Vxy is equal to vyx. And so uxx is equal to minus uyy, which finishes the proof. So uxx plus uyy is equal to 0. You can use the same argument, but use the derivatives in the opposite direction to show that the imaginary part satisfies the same equation. So if you start from here, but instead of taking x derivatives and a y derivative, you took a y derivative and an x derivative, you would end up showing that the imaginary parts are harmonic. Okay? Okay, so you should be getting the sense that since these pieces, all of these pieces that we're talking about here showed up in Calculus 4, which basically devolved into the study of path integrals of conservative vector fields, that somehow this is all really just that. And if that is the intuition that you're having, your intuition is correct. Secretly, what's going on here is these conditions correspond exactly to conservative vector fields in some sense. And so we're going to be doing, when we build the theory of integration, we're going to be building it, and the results that we're going to get are going to look like path-independent integrals of against conservative vector fields. So this is the sort of framework for that. Which again makes me, I'm like, oh man, complex analysis isn't really special if all it is conservative vector fields. But it's more special than that. It is. Okay. Well, that's, the residue theorem, the Laurent series. Like, we can do things with complex analysis that we're not going to be able to do with real variables. Yep.
Are we sure that the second order partial derivatives exist?
They have to, right?
Just because they're harmonic?
It's the holomorphicity that does it, right? Remember that to be holomorphic, to be once differentiable is basically going to force you to be infinitely differentiable.
Oh, that's right.
Right? And the structure of these things is, if these things, because of the open setness of the condition, these functions, the fact that these things are C1 is combined with the fact that the function is complex differentiable is going to force those mixed partials to exist. It's a good question. Okay, so now I stated this theorem last time that said the following. It's kind of a weird one. For each, so for any u of xy, which is real valued, and harmonic on a disk S.
Isn't real valued redundant if we're saying it's harmonic?
Yeah, but from the logical standpoint, you start with a real valued function u, and then you say the additional quality of being harmonic, right? So this is a study of real valued functions, but yes, that's encoded in the idea of being harmonic. We're just being extra pedantic. For any, there's no end of pedantry. If you guys want infinite pedantry, I can put every single detail and everything, but it sort of turns the class into a grueling slog. So some people might like grueling slogs, I don't know. For any u of xy real valued and harmonic and disk S, yes. Having my math compared to oatmeal would be sort of insulting. But, there exists a function v of xy such that v of xy is harmonic on S and f of x plus iy equals u of xy plus I of xy is analytic. Can I say that yet? Yeah, okay, I can, yeah. Analytic. On S. So the idea here is that you can use harmonic functions to build analytic functions. And I said this was true last time, but I didn't say how to do it. Yep.
I'm sorry, what does it say the x, is it the x comma y or the x plus iy?
It's x plus iy. F of z, which is f of x plus iy, is equal to this. So v of xy is called the harmonic conjugate of u. And the only part of the proof that's actually interesting at all, the proof that this is true is kind of technical and not that enlightening, except that the way that you do it is you actually construct the harmonic conjugate directly. So this is a constructive proof. And that part of the proof is interesting because it gives us a formula we can use to produce a harmonic conjugate if we start with a harmonic function. So here's the core of the proof. It says the following. Given a harmonic U, choose a point x naught, y naught in S. And then v of xy is equal to the integral from x naught to x of minus the y derivative of u sy ds plus the integral of y naught to y ux x naught t dt. There, look how clear that idea is. That's just it. This formula right here, if you are given a u, the proof actually constructs the harmonic conjugate and then shows that this thing has exactly the properties that you want it to have. And it does it, if you actually look closely at it, you can see why it does that. The fundamental theorem of calculus is going to tell you that this thing is going to force v to satisfy the Cauchy-Riemann equations. If you take the derivative of this function, uy falls out of it, right? The fundamental theorem of calculus is going to tell you if you took d by dx of this thing, this is a function in x, that the correct function will fall out. So if you're interested in actually seeing the proof that this thing gives you a piece that satisfies the Cauchy-Riemann inequalities, because the rest of the proof is basically from here, what you do is you show that u plus iv with this v that you constructed this way satisfies the Cauchy-Riemann equations, satisfies CRE. Yep.
Is the reason why there's not a y naught, there's an x naught?
Yeah, it's just because the formula works out that way.
Okay.
Like there's not the unique way of constructing it, but essentially what you're doing, I mean, I will show you why in a second. Like, I think last time what I pointed out was this is akin to the idea where you integrate a function with respect to x to figure out the potential it came from, and then you differentiate it back down again. We're going to do that, and this is what comes out of that process. So I'm going to do one example of this the hard way that you should not want to do, and then I'm going to show you how to do it the easy way. But you got to do everything bad once, at least. Otherwise, you don't appreciate the good stuff. Anyway, let's find the harmonic conjugate the hard way of this function. Let's suppose that you have u is equal to x squared plus y squared plus 6x plus 2y. How do I even know that function is harmonic? Maybe we should check. Ux is 2x plus 6, so uxx is 2. Did I miss a minus sign somewhere? I did. This is supposed to be a minus sign. Heh. And uy is equal to minus 2y plus 2, and so uyy is, fortunately I fixed the negative sign, so I've got a harmonic function. Okay, why is it harmonic? Because uxx plus uyy is equal to 0, so u is harmonic. So let's find the v. Man, should I choose a good base point here? I mean, I got to pick this base point, right? And there don't seem to be any restrictions on where this function is harmonic. So if it's harmonic everywhere, then why not choose the point 0, 0 for x naught and y naught? Choose x naught, y naught equal to 0, 0. The reason I can do that is because this equation is satisfied everywhere for this function, which means it's harmonic everywhere, which means that I can pick any point I want to be the point x naught, y naught for this formula. So I'm just going to pick 0, 0 because I don't want to compute with anything else. All right. Okay, let's write down what this formula would say. It's a good thing I calculated these partial derivatives here. So v is going to be equal to, let's see if I can write this down, the integral from 0 to x of minus uy s comma y ds plus the integral from 0 to y of ux 0 to t dt. Huh. Well, those are pretty easy in this case because uy only has y variables inside of it. So this is equal to the integral from 0 to x of minus, okay, what is uy of sy? Just minus 2y plus 2. Since there is no x's in it, there's no s's that show up in the integral anywhere. And the partial derivative of u with respect to x with 0 filled in for x and t filled in for y gets me 6. Am I wrong? Yep.
Why don't you integrate indefinitely in the theorem? Is there some like catch to that?
What do you mean? I'm going to integrate indefinitely.
I'm sorry.
All right, I'm sorry. No. Why don't I integrate indefinitely? I mean, I don't like doing indefinite integration of. The point is that the base point itself actually matters in this exercise, right?
Always?
Yeah. Because if you have like a harmonic function that doesn't include 0 in the domain, that information ends up included in the structure of the function.
Interesting.
I mean, you can see it because it's evaluated at a particular number right here, and that's not necessarily some plus c. That information is encoded in the structure of the function. So yeah, you can't just integrate indefinitely. You require this sort of definite, like this one variable definite integration. Okay, so I guess you do this, and what do you end up with? Well, given that everybody in here has done lots of calculus, I'm going to assert that this is equal to 2xy minus 2x plus 6y. Right? I mean, integrate this with respect to s, so an s shows up in here. And then put an s in some places and zeros in other places, and this will fall out. And on the other hand, I think if you integrate this, it's pretty clear. 6y is what falls out of that. Okay. If you don't remember how to do this, you can email me. Go back and look at Stewart's terrible. Stewart's dead. Stewart's terrible chapter on partial integrals.
What's wrong with Stewart?
Oh, Stewart is awesome until it gets into the multivariable section, and then it's just a hot mess. So, like, it's yeah. I mean, really, like, all kidding aside, if you actually don't remember how this goes when you're integrating in the like the sort of this partial integration idea, Stewart is good for the exercises that he has about how to do this. But if you're interested in remember the theory, I can give you sections of Colley or any of the other texts about multivariable function theory that will give you an opportunity to go back and practice this. Okay, so what I want to know is, I really hope that this thing, so the claim is, I went through this process, I did this terrible formula, I ended up with this function, and the claim now is that f of x plus iy is equal to x squared minus y squared plus 6x plus 2y plus I times 2xy minus 2x plus 6y is analytic. I built myself an analytic function by doing that. I found the correct object to be the harmonic conjugate. And I guess the idea is that you can actually just compute directly the Cauchy-Riemann equations here, right? This thing is the harmonic conjugate. This was the u that we started with. This is the v that we calculated from the formula. And if you look at ux, we already know ux and uy, right? Ux is 2x plus 6, and uy was minus 2y plus 2. And if you look at vx, you get 2y minus 2, which is the negative of this. So this part of the Cauchy-Riemann equations is satisfied. And if you look at Vy, you get 2x plus 6, which is equal to that. And so the other half of the Cauchy-Riemann equations are satisfied. So that formula is basically constructed precisely to force that equality to hold. Now you might ask, why didn't you put the plus c in this integral, right? Like, is there a plus c that's going around here? And the answer is yes, but all we really care about when we're doing this sort of function theory is like up to a constant. We're looking for the analytic function that this defines. Okay, yep.
So those CREs show that's holomorphic, right?
Yeah, I'm being sloppy. It's holomorphic. I should have figured somebody would call me out on that. Holomorphic. And yeah, secretly I'm using the idea that holomorphic is eventually going to imply analytic, right? So we don't have it yet. Yeah, by Taylor's theorem, which we have yet to prove, holomorphic is equivalent to analytic. So right now all this shows is that we have a holomorphic function. And you can anticipate in the future, once we have the Taylor theorem, we'll be able to build a series for any function that has infinite derivatives. Okay. Okay, well, I don't know about you, but I don't want to memorize that formula. It sucks. Right? So instead, what we're going to do is we're going to go back to 242. And we're going to do partial integration instead. So instead of constructing this object from this formula that came out of the proof that this was true, we can use this method. Okay, now, before I do that, do we have to actually memorize that formula that he just wrote on the board with those integrals inside of it? No. Do I have to know how to compute a harmonic conjugate? Yes. So I would expect that the way that you know how to compute a harmonic conjugate is the way I'm going to show you now, which looks like this. So we're going to compute V another way using the Cauchy-Riemann equations. And the idea is we know U, but we don't know V. So we know that U is equal to x squared minus y squared plus 6x minus, or plus 2y. And we know that ux was 2x plus 6. And we know uy is equal to minus 2y plus 2. And now this is when we invoke the Cauchy-Riemann equations. And this is where it's going to look kind of like solving for the potential of an exact field. So here, or the potential for a conservative vector field, here we know that ux is also equal to vy. That means vy is also equal to 2x plus 6. And that means v should be equal to the integral of 2x plus 6 dy. The Cauchy-Riemann equations allow us to replace the ux with the vy. So if I integrate that function with respect to y, I get 2xy plus 6y plus possibly a function of x that was destroyed by the partial derivative. Right? Because if I took a partial with respect to y of this, any function g of x would be annihilated. So now take v with respect to x. Well, v with respect to x is going to be 2y plus 0 plus g prime of x. And the idea is I know what vx is. Because It's right here. Because Vx is equal to minus Uy by the other Cauchy-Riemann equation. And so this thing that I got by taking Ux, thinking about it as Vy, integrating it with respect to y, taking the derivative with respect to x, is also equal to minus Uy, which equals minus 2y plus 2, which is equal to 2y minus 2. And look, I hope this is familiar, at least in some distant desert of a class that you long forgot, because differential equations is a class most people would prefer to forget, the first one anyway. So you just compare, right? If this expression for Vx looks like this, and this other expression for Vx looks like this, you can just solve for what g prime of x must be. 2y plus g prime must be equal to 2y minus 2. That means that g prime is equal to negative 2, which means that g is equal to minus 2x. And so what's v? V is 2xy plus 6y plus 2x, which is the same thing we have here. Minus, did I miss a minus somewhere? Minus 2x, which is the same thing we got using the formula. This way is much easier to remember if you exploit the fact that the Cauchy-Riemann equations hold, because the process is always the same. Start with the u, calculate the partial derivatives, and then just set up two new equalities with the Cauchy-Riemann equations to figure out what v must be. Because if I know both partial derivatives of v, I know v. Make sense? Okay, this way you should just know how to do. So when you're computing these things, unless in the homework it expressly tells you to compute it using the formula, you should practice doing it this way. This is an artifact of the proof. This is a method that is true because we've introduced the extra ingredient of the Cauchy-Riemann equations. Questions? Yep.
Are these unique?
They're unique up to an additive constant, right? So the analytic function up to an additive constant. It's like the same thing when you take antiderivatives are unique up to an additive constant. The same thing here. Right, the fact that partial derivatives are involved means that can't be detected and has to be picked up with an initial condition. Yep. Oh, scratching your elbow. Anything else? Okay. So you might ask, well, what's the big deal? So, okay, so you say that harmonic functions are interesting because harmonic functions, whatever, they satisfy Laplace's equation, and supposedly those are physically motivated. So one of the most interesting things about harmonic functions is they satisfy a property called the maximum principle. So to characterize this, I want you to think back to when you were taking Math 241 or Math 304. One of the grindiest, most nitpicky things you have to do is maximize a function, right? I give you some polynomial in two variables, and I say, and some square or something it's defined on, or a circle, and I say, figure out where this function attains its maximum and minimum. So then you have to compute all of the critical points, and then you check all the critical points, but then you have to parameterize the boundary of the domain that you were on, and then go searching on the boundary for the other possible places where the maxes and mins were. If you didn't do that, it's because your teacher didn't want to because it's annoying. And they just said, we're just going to ignore the boundary and look in the interior. But the idea is, normally with a function of two variables, if you have a function u of xy, just a general function, I'll make it C1, a general C1 function, so the derivatives exist. And I want to figure out where that function attains its maximum and minimum value. You have to follow this algorithm where you say, okay, well, first I have to find all the critical points, which means I have to solve those horrendous systems of equations where I have like families of curves that are intersecting each other in 5 or 6 or 8 places, which gives me all these places where there's potential maxes and mins. So this is typically an exercise in, I guess, what I would call computational algebraic geometry. And by that I mean, here's a function in x and y, and here's another function in x and y. Figure out where these families of functions cross each other, which is like curves falling all over themselves. What?
Sorry, what is it? Say
Ah!
Yeah.
Which part? Okay, I'll just go right.
Final.
You know, instead of my joke, I will write, you have to find lots of intersections. Oh, it was the other sentence you didn't agree with. Okay. Find all critical points. Which typically, you know, it's like, oh, look, one function looks like this, and the other one looks like this, and you've got to find all 4 points where those two families of curves cross each other, and then check all of those for the interior maxes and mins. And then step 2 is you have to somehow parameterize the boundary, and then check the boundary for the other possible places where the maxes and mins could be. Parameterize the boundary, and then find all of the boundary critical points. So the deal with harmonic functions, yep.
So is this a study in complex itself, like the complex analysis? Because I was wondering if you just plug into like a steepest descent like gradient.
You can't generally, because steepest descent algorithms aren't guaranteed to converge, right? And so root finding or like local, so this is like in optimization problems generally, if there are interior points, they are never guaranteed to converge because the behavior of the tangent planes can be so erratic that you might end up in a trap. I don't remember there's all names for the different traps you can find yourself in if you're running one of these like sort of root finders, right? So in complex analysis though, see complex analysis is built out of analytic functions which are built from harmonic functions, and with harmonic functions you never have to do this part. Harmonic functions eliminate the need to look in the interior, which makes optimization much easier because then you're just looking at the boundary. And you're looking at a one variable parameterization on the boundary. So it's just one variable calculus, not two variable calculus. So the deal with harmonic functions, if you add the condition that the function is harmonic, you get what's called the maximum principle. Which says the maximum and the minimum values of u of x and y occur on the boundary of the domain. So no interior optimization needs. Yep?
What if you is defined on the entire complex plane? Or group plane to prove that?
Then usually what you do in that case where you have an entire function like that, or say like an entire analytic function that gives you these harmonic functions. So you can talk about a function being harmonic everywhere, right?
Right.
Then what, like normally what the problem boils down to in that case is the typical application of harmonic functions is you're always define some disk that you're working on, right? If you want to use harmonic functions, you can never just feed in the entire complex plane, right?
Right.
An entire function is always going to be unbounded,
Gotcha.
right? There's actually, we haven't proved it yet, but there's this rule that says that if you're an entire non-constant function, yeah, basically, there's like, yeah, we'll get there. It's hard to do that, okay? And basically, if you're ever working with harmonic functions, it's always some finite domain you're working on. And the virtue is, if you draw me a circle, circles are really easy to parameterize, right? So I say, here's a harmonic function. I'm studying the harmonic function on this circle right here. Where does it have its maximum and minimum values? Well, any circle that you draw, the maximum and minimum must occur on the circle that you drew and not in the interior. And any new circle that you draw, the maxes and mins push out to the new boundary. Yep?
Isn't the studying an unwhole plane like the Cauchy problem for Laplace's equation, which is like ill-posed, isn't it?
Yeah, I mean, there's all kinds of ill-posedness that sneaks in when you do that. So yeah. Right. So, the sort of like the motivation for this comes from sort of physical applications originally. And in physical applications, you're always working on these sort of bounded setups. And so, I mean, working with harmonic functions is amazing because it means that you don't ever have to go and look around at what happens in here. And the thing about what's going to happen with complex analysis that we're going to discover after we get a couple more chapters of material is it's not just that the maximum and minimum values occur at the boundary for harmonic functions. It's that the entire behavior of an analytic function is built explicitly out of only what it does on a circle. So if you have an analytic function and you can tell me what it does on just a circle, you know every other value inside the circle too. And that's way stronger than anything that shows up in real calculus. Even the real calculus of two variables, you can never say that. So this is like, these things are incredibly useful because the behavior at the boundary dictates what happens on the inside. Okay? Okay, now you might ask, is there a similar theorem for, okay, so this thing, this U, so here's a natural question to ask, is, okay, that's great, but this is a class in complex analysis, not harmonic functions, right? What the hell does this have to do with an analytic or you know, holomorphic functions? Does this do anything with, say, holomorphic or analytic functions? Holomorphic or analytic functions. After all, a holomorphic function is built out of harmonic pieces, and the answer is yes, a very strong theorem called not the maximum theorem, but the maximum modulus theorem. So I'm just hinting that this exists, but the fact that analytic functions are built out of harmonic pieces means analytic functions attain their maximum magnitudes on the boundary of their domains also. Another incredibly useful fact. And also, like harmonic functions, or sorry, this is why analytic functions can be reproduced from the boundary. So the maximum modulus theorem says, as a consequence, that the maximum modulus, so the maximum value of the length of f, because remember, it doesn't make any sense to talk about a maximum value of a complex number because they have a real part and an imaginary part. And what does it mean to be a maximum of a complex number? So to get inequalities, we talk about the length of the complex number. The maximum value of the length of the output of f occurs on the boundary of a, I'll say finite or bounded domain. And that is incredible because it means, again, you never have to go looking in the interior if you're trying to control the size of a function. Yep?
Are these always disks whose boundaries are circles, or are they simply connected?
Well, it's really simply connected domains, but everything can be basically reduced. The fact that you're simply connected means you just reduced disks, right? It's open and simply connected. Gets you the fact that you can just say the equivalent case is that there's a circle that you can do this on. Yep?
Also mins or just max?
Well, if you're a maximum of f, you're a minimum of minus f. You just, these are real, right? This is a real function, so you just flip the graph upside down. Minimums become maximums and maximums become minimums, so you get the minimum modulus principle, or the minimum principle for free.
Oh, okay, I see.
Right? I mean, imagine, you got some surface, and here's the maximum right there, and here's the minimum, and you just turn the graph upside down around the y-axis. You've just flipped the maximum to the minimum and the minimum to the maximum. So the maximum principle implies the minimum principle.
Gotcha.
And the same thing with the modulus theorem as well. A little more subtle in this case. Because this has to be 0, right? No negatives. It's okay? All right. So that concludes our brief foray into a field called harmonic analysis. What I want you guys to take away from that is we have basically finished up our study of derivatives. So, you know, all the derivative stuff we learned was, I mean, what did we actually learn in this first sort of unit? We learned what a holomorphic function is, which is on a disk. And once differentiable on a disk implies infinitely differentiable on a disk in complex analysis. We also know what an analytic function is. Yeah, but not just a power series. An absolutely convergent power series on a domain with non-zero radius, right? So we learned about holomorphic functions. We learned about analytic functions. We learned about, what else have we taken away? The Cauchy-Riemann equations. We talked about harmonic functions. We talked about trying to think about other like material things that. Yep. We did introduce the ratio and root test. We have the extension theorem. That's really nice. Yep, the extension theorem. I mentioned it briefly. We will come back to it. There's this object called the identity theorem that I didn't spend a lot of time on. So this is not proved yet. We mentioned Taylor's theorem. Taylor's theorem was the idea that F holomorphic implies that F of Z is equal to this, the nth derivative of F at A divided by n factorial times Z minus A to the n. This is unproved, but this is basically the theorem that says holomorphic implies analytic. So that's as yet to be proved. We did prove, rather gruelingly, that analytic implies holomorphic, which implies infinitely differentiable.
Are we responsible for knowing that proof?
No. It's a great proof, but no. It's not that kind of class. Any other sort of big material pieces I'm missing here that we talked about?
Multi-valued function?
Multi-valued, that's excellent, yep. Multi-valued functions and inverses. Talked about inverse functions. We talked about the function argz and little argz. We talked about log z and little log z. Oops. Infinite. Calm down. Infinitely differentiable. We did a lot of stuff already. Basic computations like real and imaginary parts. Okay, I think that's close to all the big meat of what we've done so far. Okay, so essentially I think of this stuff as the study of derivative, the complex derivative. Things that are immediate consequences of the complex derivative. And even though, the reason why we have this unproved is it turns out to be the case that the obstruction to getting this theorem, so analytic implies holomorphic, we did. Holomorphic implies analytic would require that we have some way of computing these coefficients. The problem is that the way that you compute the derivatives is with integrals in complex analysis. So we're going to use integrals to compute derivatives. And so the study of this function is actually a study of integration, not the study of derivatives, which is why we don't have a proof yet. All right. So we're going to finish up today with a brief reminder of an idea maybe you haven't thought about in a long time. I'm going to define a set for you, a set that showed up multiple times in here. So let's look at a circle. How about a circle of radius r, bigger than 0, centered at a point z is equal to a. Question. Write me a parameterization of that circle. See if you can remember how to do it. I've got some circle. It's not open. It's a circle. It's not a disk. It's a circle. And I want to imagine that this is a circle that's centered at z is equal to a, and it has radius r. Write me a function gamma of t that parameterizes the circle. Complex function. This is a complex function. This is sitting inside of the complex numbers. This is a subset of the complex numbers. Probably not an equal subset. It's a complex numbers. So this is a circle sitting in the complex plane. And I want you to think if you can cook up a function that describes this. I'll even tell you the domain if you want. How about we let t run from 0 to 2 pi?
R e to the I t.
Okay, so r e to the it, to which my response is almost.
Plus
Because,
A.
what's that?
Plus A.
Does that do what we want? Well, if I put in 0, remember these are complex numbers, not real numbers, right? So complex numbers. I mean, the r is a real number, but the a here is a complex number. And I want you to think about this. This should be very familiar to like doing parametric functions in calculus 3. Man, we're really bigging out the oldies here, right? The idea is that when you guys did this in calculus 3, you do this parametrization with cosine and sine, right? Like or some sort of cosine and sine thing to like describe the path of a parametric, this parametric function that describes this thing has sines and cosines in it. You should think of this as a vector, and that's the angle the vector points in, and that's the length that the vector points in. And this is sort of a fixed center that you're moving vectors from. So a plus r e to the it is like saying, well, if t is equal to 0, that's like saying a plus r, not 0, but the direction that points along the positive real axis, which would put you right here. Z plus r, but that number is a real number, so really what you're saying there is that this is x plus r, comma y, is a way of thinking about it. Because r is a real number, if you're pointing out just in this direction, that's real, and it only changes the x coordinate. This idea of parameterization is going to be what we use when we start doing complex integration, because complex integration is contour integration. Or, as we learned it in Calculus 4, path integration. So we're going to do lots of path integrals. And the trick to working in complex integration is to replace curves with complex parameterizations. So that's where we're going to go next. So Thursday, we're going to talk about the rest of the homework that was about harmonic functions and the other computations that we did, the Cauchy-Riemann equations. On Friday, we're going to start launching into the theory of integration. So we're going to start with the definition of the complex integral. And then next week, we're going to get into the most beautiful theorem in all of complex analysis. It's called the Cauchy integral formula, which is amazing. And every other theorem in complex analysis basically flows from the Cauchy integral theorem. All right. See you on Thursday.